Hello everybody, my name is Graham Reeve and I'm a lecturer in mathematics at Liverpool Hope University. If you have any questions about the contents of this video or any other maths questions in general, please feel free to email me at reeveg@hope.ac.uk. So the aims of this session are not to learn about the pedagogy of maths or how to teach it, but for you to learn some new maths for yourself. So hopefully you'll learn some new maths, or at least be inspired to go away and learn some new maths on your own. Or perhaps it will inspire you in the ways that you teach maths. We all know that subject knowledge is an important part of being a teacher. In fact, it forms S3 as part of the teaching standards. But you may be thinking, it's okay as long as I stay one lesson ahead of the pupils, right? Well, sometimes you might get away with this, but just think how your subject knowledge can help you teach those higher attainers or gifted and talented, that's whatever they're called nowadays. Or what about when they change the curriculum, as they so often do? I suppose you want to teach abroad where the curriculums are different. Or maybe you want to think about becoming maths lead in the future. So it's always a good idea to stay ahead of the game in terms of your maths knowledge. But having an improved subject knowledge will help you as a teacher to reach all the learners. So whether you yourself were like the pupil on the left or the pupil on the right, hopefully you will be able to help teach both the pupils on the left and like those on the right in their mathematics. In this first video, I'm going to concentrate on geometry, but with some history thrown in for added extra interest. One method for reaching different learners is to try to teach different aspects of the subject. For example, when teaching mathematics, why not combine it with teaching history, as putting the subject into a historical context can bring the subject to life. On the right hand side you'll see the famous scene of the death of Archimedes. When the Romans invaded Syracuse in 212 BC, the Roman army was under strict orders to leave Archimedes unharmed. However, he was put to death whilst Archimedes was working on some problem, reportedly saying, "Don't disturb my circles." And the mathematics that he was working on has since been lost, so who knows what difference it would have made if Archimedes had lived. Of course, you can also combine mathematics with biology. So, for example, did you know that a fox can rotate its ears by 150 degrees? Or that an owl can turn its head by 270 degrees? Or, of course, you can combine it with sport. Angles can be used in snooker, arithmetic in darts, and many sports require the units and measure. I want you to begin by casting your mind back to ancient Egypt. Now imagine you're a school pupil in ancient Egyptian times. What kind of maths would you have learned? Both Egyptian and Babylonian mathematics was largely concerned with solving practical problems. Here we see an excerpt from the so-called Moscow Papyrus, which dates to around 1850 BC. Now the reason it's called the Moscow Papyrus is because it's currently stored in a museum in Moscow. Now the Moscow Papyrus is a set of 25 problems and solutions which may have been set to school pupils. For example, problem 19 asks one to calculate a quantity which taken 1.5 times and then added to 4 makes 10. Now, of course, nowadays we'd solve this problem using algebra, but this is before algebra was invented. So next time you're struggling with an algebraic problem, take a moment to consider those poor Egyptians who would not have had the tools that we have today. So writing this question in algebra, we'd write it like this. Say, a quantity taken 3.5 times and added 4 gives 10. So what do? We just rearrange. First of all, we take 4 from both sides to give 1.5x equals 6. And then we would divide both sides by 3/2 to give x equals 4. Now, a large quantity of the Moscow Papyrus, 10 out of the 25 problems, is devoted to so-called Pefsu problems. Now, Pefsu is a measure of the strength of beer or of bread. So Pefsu is equal to the number of loaves of bread or jugs of beer divided by the number of hecats of grain, where hecat is a measure of grain which is equal to about 4.8 litres. And this problem, problem 8, you're required to work out the equivalent of 100 loaves of bread, so strength 20 Pefsu, compared to beer of PEFSU 4, how much beard you get for the same amount of grain. I won't dwell on this question, you can read through this, but you see the method is quite complicated and all written in word form, because this is before they had algebra. So this is the kind of solution they'd have to have done to solve these problems. Maybe you could think about how you'd solve this problem using algebra. Another ancient Egyptian mathematical text that we have is the so-called Rhind mathematical papyrus, and this one dates slightly later than the Moscow papyrus to around 1550 BC, and this is currently held in the British Museum. Again, this is a series of mathematical problems, and problem 41 to 46 concern the calculations of certain volumes of cylindrical and rectangular granaries or grain silos. So suppose we have a cylinder and we want to work out its volume. Now, nowadays we would know that we would take the area of the cross-section circle and multiply it by its height h. So the formula for the volume is pi times the radius squared times by its height, where of course the radius is half of the diameter. So the formula for the volume in terms of the diameter is pi d over 2 all squared times by h. Now to solve this, or to calculate this, we have to use this special number pi. But the number pi wasn't known to the ancient Egyptians, and so they used an approximate value to the irrational number pi. They used this number 256 divided by 81. So of course this only gives an approximate answer, but for the purposes of the ancient Egyptians, this was sufficient to calculate the volume. Another problem from the Rhind papyrus was to calculate the volume of a so-called frustum, or truncated pyramid. Now the ancient Egyptians are well known for building their pyramid tombs, but they also built some tombs with a frustum shape called mastabas. Now the method they gave, the scholar Ahmes gave in the Rhind papyrus for solving this problem is as follows. If you are told a truncated pyramid of 6 for the vertical height and 4 on the base by 2 on the top, you are to square the 4, result 16. You are to double 4, result 8. You are to square this 2, result 4. You are to add the 16 and the 8 and the 4, result 28. You take 1/3 of 6, result 2. You take 28 twice, result 56, which is your answer. Now this gives the correct answer, but the formula, as you see, is very complicated. But if you follow it in modern notation, they actually give the correct formula, which we know is given by the volume is 1/3 of the height times by the dimension. If the dimension of the base is a and the dimension of the top size is b, then the formula is 1/3 h times a squared plus ab plus b squared. Now, so the method the Egyptians gave is correct, but as you see, without algebra, it becomes a lot more complicated. To summarize, Egyptians were largely concerned with solving practical problems which related to their everyday lives. For example, in farming, what area of land is needed to create a certain yield of a crop? In making bread and brewing beer, how much grain is needed? And how much material is needed for building pyramids? We've seen that for Egyptians, approximate answers were usually sufficient. No algebra was used, as this had not been invented. They only used word problems, and their solutions were often wordy. Pupils and students nowadays are often scared of algebra, but remember, it's there to make our lives easier. The solutions given by ancient Egyptians were often quite formulaic, and it's not completely clear how much understanding is needed for the student to solve these problems. And the Egyptians didn't have any proofs or any reasons why the solutions they were given were in fact the correct solution. Fast forward 1,000 years and it brings us to the time of the ancient Greeks, and in particular a man named Thales or Thales of Miletus. He is often regarded as the first mathematician in the modern sense of the word, and is the first known person to have a theorem named after them. Thales lived from around 624 to 546 BC, and he was originally from the city of Miletus, hence the name. Now, Miletus is in modern-day Turkey, but at the time was considered a Greek city. One thing that Thales is known for is his ability to predict solar eclipses. He was not the first person to do this, as this was known to both the Babylonians and the Sumerians before him. The one particularly famous event occurred on the 28th of May 585 BC, when Thales predicted that there would be a solar eclipse, quite correctly. And on this particular day, there was to be a battle between the Medes and the Lydians, who were two civilizations that existed in modern-day Turkey at the time. Now, on this particular day of this battle, when the eclipse occurred, they saw the eclipse and decided to call a truce, as they realized that the gods were probably more powerful than they were, and so they put their differences aside them. Now, the reason this is so famous is because Thales predicted this eclipse on this day. This is one of the only examples of a battle during this period when we know the exact date on which it took place. Another story about Thales goes as follows. He once apparently overheard some people saying, if he's so clever, how come he isn't rich? And given that he'd previously warned the people of Miletus about the unscrupulous behaviour of market traders who were cornering the market in various types of good or another, and then charging overinflated prices, but everyone ignored his warning. So he decided to buy up all the olive presses in the region and thus control the entire market in olive oil. And this way he made a lot of money. Apparently, after everyone heeded his warnings, he then sold all the presses and he went back to living a more frugal life, allegedly. One result which you're probably already familiar with is that vertically opposite angles are equal. And this was first shown to be true by Thales. Now, given that the angles on a straight line add up to 180, we can prove as follows. So if we're given something like this, we can find x as follows. We just to find x, we take 180 and then subtract 49, which gives us 131. Now if we label the other angle y, then this will be given by 180 subtract x. In other words, 180 take 131, which gives us 49, which is the same as the original angle. Now the fact that we started with 49 was just chosen arbitrarily. We could choose any number here. So let's give it another name. Let's just call it A for angle. And the same procedure as follows. If we have x would be 180 subtract a, then y would be 180 take away x, because again it forms a straight line. And then so if we just replace x in this equation from the previous equation, we end up with 180 subtract 180 subtract a, 180's cancel, and we have minus negative a or minus a, which gives plus a. So we see that the angle y is indeed equal to the angle a. So vertically opposite angles are equal. And this was first shown to be true by Thales. Here are some examples for you to have a go at. So pause the video now and have a go. Here are the answers. So the mathematics of Thales and also later Greeks can be seen to be very different in character to the mathematics of the ancient Egyptians. One thing to notice is the reliance on proof. Thales wasn't happy to have some formula merely stated, he wanted to see a proof, like in modern mathematics. Second thing to notice is that he was interested in mathematics for its own sake and the beauty of the geometry, not just in practical problems. However, he did solve some practical problems. For example, he was once asked to calculate the straight line distance between two cities, A and B, which were separated by a lake. And the way he did this was by pacing out a triangle that went around the lake, so 50 miles, and then measuring a certain angle, say 60 degrees. He was then able to construct a scale model, and then using the properties of similar triangles, he was able to scale up his model to work out the distance between the original two cities. Another problem that Thales was asked to do was to find how do you work out the distance between a point on the land and a ship out to sea. For example, if you want to fire a catapult at it. And the way that Thales did this was can be seen through the following diagram. Now he again uses similar triangles to solve the problem. So the siege weapon is positioned at point M, the boat is out to sea here, and this diagram is viewed from above, so the cliff edge is the vertical line here. So the first point is you have to pace out the distance to the point A, which is the point closest to the shore where the boat is. Then you pace a similar distance in the other direction, call it D, and then you walk along a straight line in the direction towards E, perpendicular to the cliff edge, until you find a point P where the boat lines up with the siege weapon in your view. And therefore you've constructed a similar triangle over here, and therefore you can pace the distance from P to M, which will be the same as the distance from M to B. One result that Fales is most famous for, so-called Fales's theorem, says that if you take a circle and then you construct a triangle where one side of the triangle is the diameter of the circle, then the angle at B, the angle ABC, is necessarily a right angle. So we end up with a right angle triangle. And Fales was the first one to prove this, and he was so happy with himself that he went away and sacrificed an ox to the god Apollo. Now, as you can see in this video, as long as one of the sides is the diameter of the circle, it will be true for all these angles. As we rotate the point B, all of these angles are right angles. So this is a nice result, but how would we prove this? Or how did Fales prove this? Well, the proof is as follows. Hopefully the proof should be fairly straightforward to follow. The first thing we need is the fact that the interior angles of a triangle add up to 180 degrees. But more on this later. So we take our diagram and we're going to draw a straight line connecting the origin, marked O, to the point B on the circumference. This divides our angle into two. Now, drawing this line, we construct two isosceles triangles. Now remember, isosceles triangles are ones that have two equal sides and two equal angles. Now the name isosceles comes from the Greek words iso, meaning the same, and skeles or skelos, meaning legs. So an isosceles triangle literally means same legs. It has two equal legs. And if you imagine a person standing with their legs apart, they would form an isosceles triangle. So we refer to these equal sides as the skelos or legs of the triangle. And over on our circle picture, you see the two lines, one joining O and A and the line joining O and B, are of equal length because they both join the center to the diameter, to the circumference of the circle. Similarly for OC, so all OC, OB and OA are all the same length. Consequently, the angles are all the same. This is an isosceles triangle, so the ones marked Y, coloured in blue, are equal. This is this triangle, and the other isosceles triangle gives us the two angles marked in red and labelled X, are also the same. Now we use the fact that the interior angles of a triangle sum to 180. So the angles of the large triangle, we add them all up. We have X plus Y plus Y. This triangle would give the sum of 180, so these all add to 180. Now if we collect like terms on the left hand side, x plus x, same as 2x, and y plus y is 2 watts of y. So we have 2x plus 2y equals 180. Now we divide both sides by 2, giving x plus y equals 90. So the sum of the two angles, the red and blue one at the angle at the point B, is equal to 90. In other words, the angle ABC is a right angle. Now there's nothing special in our assumption about the point B. We could have put that anywhere on the diameter, on the circle. So this is true for all circles and for all points on the circle. As we made no special assumptions about the radius of the circle or the point or where the point B was. So the proof works for all circles and all triangles where one side contains the diameter. And this is the proof. Now the last result of Fales I'm going to talk about is how he calculated the height of the pyramid at Giza, which was hitherto unknown. And he did this by measuring its shadow. For example, if you put a stick in the ground of, say, length 1 meter, if you wait until the shadow is 1 meter, then you know that the length of the shadow is the same as the length of the stick. So at that time, if you measure the length of the pyramid shadow, you will obtain the height of the pyramid. Now, of course, if you take it at another time when you didn't have the sun making an angle of 45 degrees with the stick or the pyramid, you could obtain a different length shadow, and then you can work out the problem similarly using ratio. And you might like to use this when teaching. I'm reminded of the quote from the mathematician David Mumford, who said, "I tried, unsuccessfully it might add, to get each high school in which my children were enrolled to go outside during geometry and find out how tall the oak in the yard really was." And you can do this very easily just by measuring length of the shadow of a stick, and then if you find the ratio of the length of the stick to the length of its shadow, for example here we have a 2 meter stick, or it looks like a lamppost, isn't it? But a 2 meter stick, if the shadow is 75 centimeters or 0.75 meters, if you do height 2 meters divided by 0.75, you get 2 2/3. So in other words, the actual height is 2 2/3 times longer than the shadow. So the height of the tree is also 2 2/3 times the length of its shadow. So you do 2 2/3 times 8, which is 21 1/3 meters. Similarly, you can apply the problem to find the length of distance across a river, so for example A to B, by constructing the following diagram. But I'll let you read that on your own. Pause the video and study the diagram. Fast forward a few years, we come to this guy, Euclid of Alexandria. Here we see modern day Alexandria, and Alexandria is perhaps most famous for its library, which most famously burnt down. But interestingly, Euclid is not believed to have come from Alexandria, despite being called Euclid of Alexandria. He was actually believed to have been born in the city of Tyre, which is located in modern day Lebanon. But it is likely that he worked in Alexandria during his life. Now, the geometry of Euclid is quite different from that of Thales. In about 300 BC, Euclid wrote a book called The Elements, which was a book that was to become perhaps one of the most famous ever written. And in this book, he stated 5 postulates on which he based all of his theorems. And Euclid is often credited as having invented the axiomatic approach to mathematics. Now, the axiomatic approach starts with some basic assumptions which no one could refute, no reasonable person could refute, and it's from that that you build on and produce more complicated theorems which follow logically. So he assumed that the following is possible. So he assumed it's possible to draw a straight line segment from any point to any other. He also assumed that any straight line segment can be extended indefinitely in one or the other direction. He also assumed that a circle can be described of any center and any radius. He also assumed that all right angles are equal to each other. Again, this seems to make sense. And most of these would seem fairly innocuous, or any reasonable person would assume that this is true. So then if you assume these are true, what can you deduce from this is the approach. So these are all fairly straightforward. And the final 5th postulate was, if a straight line falling on 2 straight lines make the interior angles on the same side less than 2 right angles, if produced indefinitely, meet on that side on which the angles less than the 2 right angles. Now this last postulate seems slightly different to the other two. It seems to be the odd one out, and indeed it is. So the 5th postulate, what does it say? Essentially it says that if you have 2 lines and then you have a line, and then if you So Euclid then went on to fill 13 books full of theorems, like the fact that you can draw an equilateral triangle, many of which you will remember from high school. So, for example, in book 3, he proves, proposition 21, he proves that if you have a segment, BD, then the angle BAD is equal to the angle BED. So Thales' theorem is a special example of this, where BD is the diameter. Another result, this time same book, proposition 18, was that if you have a circle and if you have a line that touches the circle and then you draw another line, so this line ED, and you have another line FC, then going from the center to the point where it touches, this forms a right angle. Again, another theorem of Euclid. Another result is if you have a quadrilateral inside a circle, then the sum of opposite angles, so BAD plus BCD, for example, will sum to 180. And ADC plus ABC is also 180. So these are the kind of things you may remember doing in high school. That was all proved by Euclid. He also did some other things you may not be familiar with, and in 3 dimensions. But it's well worth looking at Euclid's book and seeing some circle theorems that you remember from school, and maybe some that you don't, or that you didn't do. So his book was very successful, and in fact Euclid's Elements subsequently became the basis of all mathematics education, not only in the Roman and Byzantine periods, but right up to the mid-20th century. And it could be argued that it's the most successful textbook ever written. Here we see some older versions. Here it was studied in the medieval period, and here's some medieval version. And according to Bunt, Jones and Bedient, next to the Bible, Euclid's Elements is the most widely spread book in the Western world. But back to that pesky 5th axiom. That is, if you have, well, you remember the axiom, if you have a straight line, if you have 2 straight line segments and you extend them, they will meet if and only if the interior angles on that side add up to less than 2 right angles, less than 180. So clearly this axiom is different from the others, it's not so obvious. And many people over the years tried to deduce this from the other 4. How can you prove this result just from the first 4 axioms? And every time they thought they'd had it, it turned out to be wrong. They managed to find equivalent statements. For example, Wallis in 1663 proved that to each triangle there exists a similar triangle of arbitrary magnitude. So this is an equivalent statement to the 5th axiom. Another famous one, so-called Playfair's axiom, is that given a line and a point not on the line, it is possible to draw exactly one line through the given point parallel to the line. So you have a line and a point not on the line. You can draw exactly one line parallel to it that passes through that point. Again, that seems fairly obvious, but it can't be proven from the other 4 axioms, or so it would seem. But it's equivalent to this other statement, number 5. Another equivalent statement is that the sum of angles in the triangle is equal to 2 right angles. So the fact that we all know and love that triangles, angles add up to 180, this is equivalent to the 5th postulate. This was due to a famous mathematician called Legendre in 1774. And he spent 30 years trying to prove this 5th postulate from the other 4. Okay, so you may be thinking we can prove that a triangle, the angles add up to 180 degrees. And so you're all familiar with this fact. So we all know that, so first of all, a circle contains 360 degrees. Now this just comes from the definition. Why does the circle have 360 degrees, you may ask? Well, the reason we choose 360, we could have divided the circle up into any number of degrees. It's just an arbitrary measure. But the reason we choose 360 is because it's a nice round number. And 360 has lots of divisors, for example. So in other words, there are lots of numbers that go into 360. So you can divide a circle up into if you half it, you get 180. Half it again, you get 90. Half it again, 45. And you can divide 360 by 2, by 4, by 6, by 12, by 8, by or 36, by 10. Many different numbers you can divide your circle up into. And this is why 360 is chosen. So if a circle is 360 for a full turn, then a half turn will be 180. 180. Hang on, oh, right, terrible. 180 degrees. And so, how can we convince ourselves that a triangle has 180 degrees? Well, you may have seen this before, but this is something you can show your class perhaps. If you take a triangle out of paper, if you rip off all the corners and then put them together, so you rip the corners off, put them together, you can make a straight line. But does this prove that it's true for all triangles? We've shown it for this triangle, but how would you do it for all triangles? You'd have to make all possible triangles out of paper, which is not possible. So this may be a nice demonstration, but it's not a proof. But you can prove it as follows. So we prove the theorem as follows. So we take two parallel straight lines, and then we construct an arbitrary triangle by drawing two lines that intersect these parallel lines. Now, given that these lines are parallel, we have what's called the corresponding angles. So these two are in red, and from the fact that these lines are parallel, it means that these angles in red are equal. Similarly, these angles in blue are also equal. These are called alternate angles, or Z angles. So these two are equal, and then finally, this angle, the missing one, we mark in purple. Now you can see from this diagram, the top angle, we have that red plus blue plus purple is a straight line, so it's 180 degrees. Which means if red plus blue plus purple is 180, it means the interior angles of this triangle also adds up to 180 degrees. And so the result that the interior angles of a triangle add up to 180, we need this fifth axiom about parallel straight lines. And as Legendre showed, this is equivalent to it. Okay, so this troubled mathematicians for a long time. So during the 18th century, elementary geometry was engulfed in the problems of the parallel postulate. A guy called D'Alembert in 1767 called it the scandal of elementary geometry. But the first person to really come to understand the problem of the parallels was Gauss. So he began working on this problem when he was only 15. And he first attempted to prove the parallel postulate from the other four, like many others. But by 1813, he'd made very little progress. So he wrote, "In the theory of parallels, we are now not any further than Euclid, and this is a shameful part of mathematics." So by 1817, Gauss had become convinced that the fifth postulate was independent of the other four, and he began to work out the consequences of a geometry in which more than one line can be drawn for any given point parallel to a given line. So he said, what happens if the fifth postulate isn't true? But Gauss never published this work, and perhaps he considered this result too controversial. So despite being perhaps one of the greatest mathematicians of all time, Gauss was quite shy about publishing controversial material. And this is not the only example in history where he did this, where he shied away from publishing stuff. So if we ignore the fifth postulate, as Gauss did, we actually end up with two new geometries, so-called hyperbolic and elliptic geometry. Okay, so consider the following problem. Imagine you walk 100 miles south. You then turn left, so through 90 degrees. So you walk 100 miles south, and you turn left, and walk another 100 miles in a straight direction. You turn left again, and walk a final 100 miles. And you find you end up exactly where you started. And you find a bear sitting there where you left. The question is, what colour is the bear? Think for a moment. How could this be? So you've walked 100 miles, you've turned left, 100 miles, left, 100 miles. So you've covered three sides of a triangle. But you seem to have gone through a triangle in which you've turned through more than 180 degrees. So how could this be? Well, the only way this could be, given that you started off due south, was if you started on the North Pole. So you start on the North Pole, 100 miles south, turn left, 100 miles, turn left again, another 100 miles. And you see the interior angles of this triangle on the curved surface of the Earth, the angles, because we've got two right angles already, whatever this angle is, add on to 180, means that your triangle has interior angles summing more than 180 degrees. So if you allow triangles to have more than 180 degrees, you're in fact considering elliptic geometry, like on the surface of the Earth. Similarly, so the answer to the question is, of course, the bear is white because you're at the North Pole. And similarly, if the angles here add up to 180, can we have a world where the angles add up to less than 180? And the answer is yes. For example, you can imagine living on the surface of a saddle or on a Pringle, for example. And you'll find if you draw a triangle on a Pringle, the angles add up to less than 180. So if you're interested in finding out more about hyperbolic, so these are so-called non-Euclidean geometries. You have hyperbolic and elliptic geometry. There's lots of YouTube videos available, and you can even explore hyperbolic space in VR through this explanatory YouTube video, and then you can play online here and explore the hyperbolic world, hyperbolic 3D world. And here's another interesting video interesting video on the history of non-Euclidean geometry. Okay, so I'll stop there, and thank you very much for your attention. If you have any questions, please email me at reevg@hope.ac.uk. Thank you very much.